Hello everyone, welcome back to Math 143, Finite Mathematics. So today we are going to continue the simplex method. So we discuss up to choose the pivot column, pivot row and pivot entry. Once we found the pivot element, our goal is to make its column looks like a unit column. Right? So before that, let's move towards the simplex algorithm, the summary. First, set up the initial simplex tabulo and check the bottom row, all non-negative. Then we can find out the optimal solution. If not the optimal, that means choose pivot element, perform the row operations and repeat until the optimal solution. And final, read the solution. But today we are going to discuss this simplex algorithm. Okay, once we found the pivot element, our goal is to make its column looks like a unit column. So next step, performing the pivot, right? So once we have found the pivot element, our goal is to make its column look like a unit column. So there are two steps that we wanted to follow. Two steps. The first step, divide the pivot row by the pivot element. So it provides the pivot element equals 1. So step 1, divide the pivot row by the pivot element. So the pivot becomes 1. And step 2, use row operations to make every other entry in that column equal to 0. Use row operations to make every other entry in that column equal to 0. So this should remind you a Gauss-Jordan elimination from chapter 2. So we were using the same row operations and we are going to use the same row operations, but now our goal is to improve the objective function. Right? Let's work through the example continuing in 1a. So example, we have x, y, s1, s2, p constant 1, 4, 1, 0, 0, 12, 1, 3, 0, 1, 0, 10, negative 2, negative 4, 0, 0, 1, 0, right? Okay, so we choose that the pivot column here, pivot row here, pivot entry here. The first, we wanted to convert that pivot entry into 1. So make the pivot element equal to 1. To do that, divide the row 1 by the pivot element 4, goes to R1. This is make the pivot element 1, right? Okay, so 1 over 4, 1, 1 over 4, 0, 0, and 3. All others remain unchanged. Okay, next step, make all other entries in the pivot column. That means this column, make all other entries, this one and this. There are 2 more elements equal to 0. So perform the row operations again. Perform R2 minus 3R1 goes to R2. X, Y, S1, S2, P constant. 1 half, 1, 1 half, 0, 0, 3, negative 2, negative 4, 0, 0, 1, 0. So then perform the entries. R2 minus 3R1 goes to R2. Then 1 over 4, 0, negative 3 over 4, 1, 0, and 1. Also perform, now we wanted to convert this negative 4 into 0. To convert this negative 4 into 0, perform R3 plus 4R1 goes to R3. X, Y, S1, S2, P constant. Okay, negative 1, 0, 1, 0, 1, 12. Okay, then look for the bottom line. Look for the bottom line. So check the bottom row. So if there is still a negative coefficient, repeat the process. That means repeat the process, find in the pivot entry, pivot column, pivot row, and do the all steps afterward. So if every coefficient in the bottom row is non-negative, the solution is optimal, right? So after this, check the bottom row. If there is still a negative coefficient, repeat the process. Repeat the process. That means find pivot column, row, and entry. Also perform the pivoting process, right? But if every coefficient in the bottom row, is non-negative, the solution is optimal. Then we can find out the solution, right? Okay, check for the bottom row. The bottom row, when we check the bottom row, what happened? We can see that there is a non-negative value, right? Therefore, we wanted to repeat the pivoting process, right? Okay. Okay. First, identify the most negative column and take the ratios. Three over 1/2, 12, 1 over 1/2, 4. So the smallest ratio is here, then pivot column, pivot row, and pivot entry here. Right? Okay. So now then, new pivot column is X, new pivot row is second row, pivot entry is 1 over 4. So then let's repeat the process again. So now we have X, Y, S1, S2, P, and constant. One over 4, 1 over 4, 0, 0, 3, 1 over 4, 0, negative 3 over 4, 1, 0, 1, negative 1, 0, 1, 0, 1, 12. Okay, then perform the row operations. First we have the pivot entry 1 over 4, then convert it into 1. Do that. Perform row operations. R2 times 4 goes to R2. Okay, all others remain unchanged. One, 0, negative 3, 4, 0, 4. Okay, then we wanted to convert all other entries in that column equals 0. To do that, R2 plus R3 goes to R3, and R1 minus 1/4 times R2 goes to R1. So you can do it once. R2 plus R3, then 0, 0, negative 2, 4, 1, 16, 0, 1, 1, negative 1, 0, 2. Okay, so no negative anymore at the bottom. No negative anymore at the bottom. No, we have one negative value here, right? R2 plus R3, yes. We have one negative value here, then repeat the process. So repeat the process again. Ratio. Non-negative entries. Therefore, this, right? Okay, then we don't want to convert this pivot entry into 1. Just remove all other values. All other values means here we have pivot entry 1, so we don't want to convert it into 1. So we wanted to remove negative 3. We wanted to convert negative 3 into 0, negative 2 into 0. Okay, let's do that again. New pivot. This would be pivot column, S1, pivot row, and pivot entry. Then perform. 3 times R1 plus R2 goes to R2, and 2 times R1 plus R3 goes to R3. X, Y, S1, S2, P, constant. 0, 1, the first row remain unchanged because our pivot element is already 1. Then perform the row operations. 3 times R1 plus R2 and 2 times R1 plus R3 . Okay, so now no negative anymore at the bottom. So check for the bottom line. So no more negatives. Therefore, we reach the optimal solution. Then, how to read the solution? Once the tabular is optimal, reading the solution is actually very easy. So let's see, reading the solution. So basic variables take their values from the constant column. Once the tabular is optimal, basic variables at the end, the basic variables, that means unit columns, take their values from the constant column, and non-basic variables are 0. So that means all other columns other than unit columns are 0. The value of the objective function is found in the last row. The value of the objective function is found in the last row. So what are the values of x, y, s1, s2 and p? Continue the example, then let's get our example here. Okay. Then what are the values of x, y, s1, s2 and p? Okay, then always identify the basic variables first. Here you can see the unit columns. X only 1 and all other entries are 0. S1 a unit column, P a unit column. So reach the basic variable columns, then you can see that 1 appears here, that corresponding constant term here. So therefore x equals 10. And also you can see 1 appear here, that corresponding constant term here. So S1 equals 2. You can see that 1 appear here and 20 here. So the last row, which is for the objective function, so P equals 20. All other columns, that means Y and S2, non-basic, are 0. Y equals 0, S2 equals 0. The optimal solution is the optimal solution is P equals 20 at x equals 10, S1 equals 2, Y equals 0, and S2 equals 0. Okay, this is how we can complete the simplex tabular problem. Right, so all the examples we discussed here. So then you should practice the 3-variable simplex method. 3-variable simplex method. So it is important to practice the simplex method. Now I would like you to pause the video and try the exercises at the end of the notes. First, rewrite the constraints with slack variables. Rewrite the objective function. Construct the initial simplex tabulo. Identify the basic and non-basic variables. Find the first pivot element. And afterward, do the pivoting things. So, before we finish, let's review a few common mistakes. So, forgetting to reverse the inequality sign when multiplying by a negative number would be a common mistake. And forgetting add slack variable to every less than or equal constraint. And choosing the wrong pivot column. Remember, choose the most negative entry in the objective row, the bottom row. And using a negative pivot entry when calculating the ratio test, only positive pivot column entries are used. Forgetting to check the bottom row after each pivot. So please don't do that common mistakes. Okay, so let's summarize today's lesson. Today we introduce the simplex method and learn why it is needed for solving larger linear programming problems. We discuss how to rewrite a problem in standard maximization form. Introduce stack variables. Build the initial simplex tabulo. Identified basic and non-basic variables. Selected the pivot element and performed simplex pivots. So remember the big idea, the simplex method follows the same philosophy as the graphical method. It moves from one corner point of the feasible region to another. But it does so using algebra instead of graphs. In our next lecture, we will continue solving simplex problems by carrying out multiple iterations until we reach the optimal solution. Thank you for watching, and I will see you in the next lecture.